Vapor pressure. In this video we're going to examine the contribution that water in its gas phase makes to atmospheric pressure. So consider a gas above a plane surface of liquid of the same type of molecule. In this case we'll be considering water vapor and liquid water. Molecules are continuously transitioning from the liquid to vapor phase, which is known as evaporation, and from the vapor to the liquid phase, which is known as condensation. Shown in this figure are water molecules in the gas phase in red and water molecules in the liquid phase in blue, and as shown, the arrow for the evaporation is larger than that of the condensation. Evaporation, unlike boiling, is only a surface process. So boiling occurs throughout the body of a liquid, whereas evaporation only occurs at the surface of the liquid water body. This is because the molecules in the liquid phase have a spectrum of speeds, and some of them obtain a high enough energy to escape from the liquid phase into the vapor phase, and likewise in the vapor the molecules have a spectrum of energies, and some of them lose energy such that they can be trapped and absorbed into the liquid phase. We'll define vapor pressure then as the partial pressure exerted by molecules of water vapor. The ideal gas law for a gas consisting of just water vapor is shown here. E is the vapor pressure in hectopascals, or in the equation it will be in pascals, but we'll typically measure it in hectopascals, by the volume is equal to the mass of vapor by the specific gas constant for vapor by the temperature. And the specific gas constant for vapor is 461 joules per kilogram per Kelvin. Saturation is defined at the state where at a given fixed temperature the water vapor is in equilibrium with a plane surface of liquid water. And what that means is that the rate of evaporation is equal to the rate of condensation. E is equal to C. The phrase saturation is a rather unfortunate expression because it brings to mind images of sponges being saturated with water. Of course, this isn't the case physically. Saturation occurs when the rate of evaporation is equal to the rate of condensation as defined over a plane surface of liquid water. And so air where the evaporation rate is greater than the condensation rate is said to be unsaturated. And we can also have supersaturated air where the rate of condensation is greater than the rate of evaporation. The saturation vapor pressure, ES, which we'll also measure in hectopascals, is defined as the partial pressure at a given fixed temperature of water vapor when it is in equilibrium with a plane surface of liquid water. For different fixed temperatures, the saturation vapor pressure varies according to the approximate Clausius-Clapeyron equation, which we won't derive here, but is shown below. 1 on ES, dES dt, so the rate of change of the saturation vapor pressure with temperature, is approximately equal to L subscript LV, that is the latent heat of vaporization, divided by RV, the specific gas constant for vapor, by T squared. Remember, latent heat is the amount of energy required to change the phase from, in this case, from liquid to vapor, and that occurs at a constant temperature. Typically, LLV is 2 to 3 by 10 to the 6 joules per kilogram. We can integrate this equation, the Clausius-Clapeyron equation, or its approximation. So we manipulate the equation, so we multiply through by dt, and then integrate over these dummy integration variables indicated by the dashes. So the ES dashed over ES is integrated from ES0 to ES, and on the right hand side we have the integral from T0 to T of dt dashed over T dash squared. The integral of the left hand side is a natural logarithm, log of ES minus log of ES0, which may be rewritten as log of ES on ES0, and on the right hand side we have a minus 1 on T, and we get rid of the minus sign by flipping the terminals of integration. So that's written as LLV on RV, all outside of 1 on T0 minus 1 on T. And then if you take the natural exponent of both sides, you end up with that exponential expression shown. And we can calculate or measure in the laboratory at a temperature of 273.15 Kelvin or 0 degrees Celsius, the vapor pressure is 6.11 hectopascals. So the final form of our equation for the saturated vapor pressure is 6.11 E to the power of 5417 outside of 1 over 273.15 minus 1 on T. So as the temperature increases, we can see that the saturation vapor pressure will also increase. And that's shown in this plot here. So we have at 0 degrees, the saturation vapor pressure is 6.11 hectopascals, and at 100 degrees Celsius, the saturation vapor pressure is 1013 hectopascals, which is approximately equal to the normal atmospheric pressure, which is why water boils at 100 degrees Celsius.